So let's derive Gauss's law of electricity from Coulomb's law. And if you recall, Coulomb's law is that the force on 1 from 2 is equal to k q1 q2 over r squared times r2 hat. All right. Now from this, we had the meaning of the electric field. So the electric field is you divide by a point charge and you end up with kq over r squared r hat. So if Q is positive, it's going away from the charge. If it's negative, it's going towards the charge. So imagine that I have some charge Q here inside a surface. This is a three-dimensional surface. And I want to take a look at a particular patch of surface right here. We're just going to call this dA. And the electric field that's coming from Q. Now, when you generally do derivations, you assume Q is positive in terms of all the drawing and the conceptually, and then if it's negative, you just pop a negative sign in there and everything reverses. So the electric field is going off in that direction right there. And the area vector is perpendicular to the surface. So Gauss's law of electricity says that the total electric flux through a closed surface, in other words, E dot dA, I guess that should be dA, is equal to the total enclosed charge over epsilon sub naught. That is what we're trying to go with. If this is true right here, then the derivative of the electric flux is equal to E dot dA. Now the electric field is going away from the charge, so we can, without any loss here, assume, since I can make my coordinate system whatever I want for convenience, I'm going to go ahead and make that my origin right there, and therefore this is the same direction as a radial vector, and so this becomes the electric field times r hat dot dA. And so if I integrate to find the total electric flux, it's the integral of E r dot dA. Probably could have done that in fewer steps, but there we are. This right here is the projection of the area vector along r hat. In other words, if we sort of expand that, so I have Q right here, and I have dA, so if this is my dA right here, so dA is going this way, so it's dA hat, and my r vector is going from my origin out that way, so that's our direction of r hat. So this is the projection along here. So that is r hat dot dA. So why don't we go ahead and make this bit right here, we'll call this dA prime. If I look at this tiny little piece right here, I basically have a solid angle. Now let's take a moment on solid angles. If you recall, for a circle, start out with a 2-dimension. I find this the simplest way of dealing with it. So if I have r here, I have some angle here, and I have some arc length here, s. I know that s is equal to r theta, assuming theta is in radians. Well, if I go into 3 dimensions, I now have, and I have some sphere. If this little patch here is dA, the angle that is subtended is going to be equal to, well, that's my surface area, that corresponds to S, is equal to r squared d capital omega. So this right here, this angle right here is d omega. That is the angle that's subtended by that little patch right there. If we look at a full circle, then dA over r squared, where the radius of the circle is r, is equal to d omega. And if we integrate, we end up with 4 pi r squared over r squared is equal to omega. In other words, 4 pi. So the solid angle for an entire sphere is 4 pi steradians, abbreviated SR. So this is the relationship we want at the moment. Since this is prime is the part that is perpendicular to r here, this is equal to the integral of E dA prime, which is the integral of KQ over r squared dA prime. That is constant, so that can come on out. Matter of fact, Q is constant also, so that comes out too. So this becomes KQ integral of dA prime over r squared. Since I want to find the flux over the entire surface, this is the flux through that tiny bit of surface, but if we want the flux through the entire surface, then we integrate over the entire area. And so the electric flux is KQ integral over the entire surface dA prime over r squared. From our relationship that we talked about, this one right here, I know that dA prime is equal to r squared d capital omega. Because remember, when we're dealing with this relationship here, this was assuming a sphere. This was assuming that A was perpendicular to omega, which we have right here. And so dA prime over r squared is equal to d omega. So we can pop that in, and so I get KQ integral d omega over the entire surface. Or actually at this point, not over the surface, but over the entire angle that's subtended, which is equal to KQ times 4 pi, which is the number of steradians around a sphere. And so I'm left with 4 pi k times q. Now 4 pi k, this is, I know that 1 over 4 pi epsilon sub naught is equal to k. Again, this is Coulomb's constant, or the electrostatic constant. This is the permittivity of free space multiplied by 4 pi, and I have 1 over epsilon naught is equal to 4 pi k. And so now this becomes the enclosed charge over epsilon sub naught. Now, if I have multiple charges, I would do it for each of them, and flux just adds up, so it's the flux of one plus the flux of the other. So if I have multiple charges, then the total electric flux would be the sum of all the individual fluxes, I equals 1 to however many charges I have. And ultimately, this just ends up being, therefore, Q1, the sum of all Q sub I over epsilon sub naught, times however many charges you have, which is 1 over epsilon sub naught times the sum of all the charges, which is just the total enclosed charge over epsilon sub naught. Another way of looking at this when you're dealing with flux, if I have a surface right here and I have sort of my electric field going through it, then I have a measure of the flux. Is the one way of looking at it is the number of electric field lines that pass through the surface. Well, if I just tilt the surface, so that the electric field is still going through, just as many electric field lines go through it, even though this is at an angle, that the flux is still going to be the same. Because ultimately you're going to do a dot product. You're looking at just the part that's perpendicular to it. So having this at an angle does not upset the amount of electric flux going through it. And so therefore, if we take a look at the, a strange shaped surface, that point when, so if we take a look here at this bit right here, where suddenly I went from A to A prime, I have not done anything in funky math. There was no sleight of hand there. It's just the flux only cares about the part that's going through the surface, and putting the surface at an angle, as long as the same number of electric field lines go through this surface right here, this dA prime as dA, we're good. So that's a little bit more formal look at Gauss's law of electricity. It is as accurate as Coulomb's law is. So if Coulomb's law turns out to be false, then Gauss's law of electricity probably need to take a look at. However, this seems to hold up pretty well.